Value stream maps graphically represent process flow as it is actually performed. VSM is typically built following a visit to Gemba, where things are really happening, in order to depict what is really going on, rather than theoretical process described in standards and procedures. This approach and VSM concepts are excellently described in Learning to See by Mike Rother. To follow the value stream, you can follow a product along the manufacturing line or a customer order along the administrative value stream, like in staple yourself to an order. Value stream maps are typically designed to flow horizontally, left to right. When a value stream is complex, it becomes difficult to view the whole picture. It may require several pages, and this makes it difficult to follow. Making the VSM vertically allows us to visualize complex value streams in a single page. Another common practice is to map the value stream by sticking post-its on a wall or large wrapping paper. This method has the advantage of simplicity. All participants write post-its in parallel and stick them on the right sequence on the wall. Sequence can easily be changed just by moving post-its. Swim lanes can be drawn to specify who's doing what. A dedicated room is sometimes used, called Obeya or War Room, to house the value stream map. Every time there is a change of hands, there is an opportunity for waiting time. Therefore, the VSM should clearly indicate who does what. A common paradigm today is that operators are good at handwriting, but may have problems with typing. I suggest an experiment to see if this paradigm is still valid today. Pick a line operator at random and ask him to type a piece of text in his phone, measuring the time it takes. Ask the same operator to handwrite the same text in a post-it and measure the time. Now ask someone else to read both messages. Which one was quicker? Which one was easier to read? The wide use of smartphones today by everyone may have changed this paradigm. The Obeya Room used to build the VSM is blocked and can't be used for other meetings or activities. It becomes impractical to save all the work done to continue working on it later on. All the work done during several hours often ends up in a long roll of brown paper with post-its, stored in the cupboard, which no one looks at it again. It is also difficult to communicate to others. Photos of handwritten post-its are difficult to read. Some value streams involve several remote locations, so a physical obeya is not practical. If you ask other people not present in the VSM exercise to give their input, they cannot view it clearly and propose modifications to the work you have done. An alternative to the post-it approach is to build a VSM in a spreadsheet with the help of PCs, tablets, or smartphones. You can draw your VSM directly using Google Spreadsheets in Google Drive and give write access to your document to all participants in the team. And it will take shorter to build the VSM than if you have to write and stick the post-its. You can even have team members participating from remote locations. People nowadays are quicker and more skilled at typing into their smartphones than handwriting post-its, especially if someone else has to read them. They can easily type while they discuss the VSM with the team. You can use a virtual Obeya room to house the VSM and use as required a room with a projector as physical Obeya. During the initial VSM construction. The first step is to go to Gemba. The team has a good look at what is going on, and then they gather in a room where the VSM is being built. It is projected on the wall, large screen if possible. All participants write the process step descriptions with their portables or smartphones into the spreadsheet in Google Drive that is visible on the wall. Typing into the spreadsheet can also be done with voice using the smartphone. That's how I do it, since I am not good at typing. The VSM can also be built directly in the cloud while visiting the line with a smartphone of the participants. In this group exercise, it is easy to make changes in the sequence, insert new steps, etc. At the end of this process, we have a workable VSM agreed to by all participants, which represents the current state as seen in Gemba. After the current VSM is concluded, we give write access to all process participants, including those who were not present in this elaboration. In this way, they can make modifications to make sure the VSM reflects what is really going on in Gemba. We might discover that we have more than one process. For instance, the night shift is doing it differently. Google Drive keeps track of who has made what modifications. We also give read-only access to the VSM in the cloud to other people and plot an A1 size copy to stick on the wall of the department or line. We keep backup copies of the different stages in the modifications to make sure we can go back to a previous version. I find it very useful to indicate who does what in the VSM instead of making another separate document. In order to do this, we include participant swim lanes on the top headers, which are easily filled while building the VSM. In the example above, you can notice that the switchboard participants in the process on several occasions. More complex VSMs with feedback loops can be done with Excel, such as this one. Download this Excel simulator from OneDrive by clicking on the QR code. In a complex process as the one above, Google Drive is not able to manage the graphic flow chart, so it's best to use Microsoft's OneDrive. The team involved in the VSM exercise can be located in remote locations, and they can all share a spreadsheet in the cloud, communicating via Zoom, Meet, Teams, etc. To ensure your VSM represents the current reality, hidden factory, rather than a theoretical process flow, you need to validate your VSM with all other participants who were not in the room, line operators, suppliers, maintenance, etc. You cannot start improving until you are certain of what the current reality is. This is easily done by giving them access to the VSM in the cloud. All the work done is not lost at the end of the meeting, and it can be updated remotely at a later stage by all process participants. You can easily keep track of the different versions of the VSM as you implement your improvements, and you can go back to the previous version if something goes wrong. You can go to Gemba with your VSM on your tablet or smartphone and directly enter process times, WIP, etc. on your VSM in the cloud. Excel allows the addition of the process parameters for each process step by adding as many columns as required on the right. After we all agree with the value stream map, we need to collect the data. For a sample process, if no data is available, we can manually collect the data in the line. This will give us a rough estimate of process times of each step. Collecting WIP data manually may not be very useful, since the values may vary widely depending on the moment we visit the line. Process times may also have significant variation. Ideally, we must define data collection points along the process and collect data automatically if possible. If data needs to be collected manually, we can use a barcode scanner to read the product serial number on each point, and the current timestamp can automatically be collected in the spreadsheet. We can analyze this collected data with pivot graphs. After we have agreed on the VSM flow, who does what and when, we need to go back to Gemba to collect process times and WIP data for each process step. If we use the Excel approach, we can access the VSM we have just produced and directly enter the numbers in our spreadsheet with our smartphones. It is easy to share this work among all participants, each taking care of a few process steps. They can all write simultaneously into our VSM in the cloud. We enter average process times in column K and standard deviations in column L. We enter percentage of yes data in column N. Average time to receive a product is 2 minutes, and its standard deviation is 1 minute. On average, 20% of products received for repair are under warranty. Average inter-arrival cycle is 5 minutes. Therefore, this is the Takt required for a complete repair line. Looking at the inter-arrival times histogram, we notice they follow an exponential distribution, something quite typical, while operation times are close to normal distributions. From this analysis, we can enter average inter-arrival time in cell K3. To have a balanced line, cycle time of every step should be below the takt time, which is the inter-arrival cycle. Average measured repair cycle of 531 is a bit larger than the target of 502, which is the takt time defined by the average inter-arrival time. Complex processes require often feedback loops. For instance, repair failing items and test them again. These loops are an essential part of the VSM because they often become the bottleneck for the total value stream. When the process doesn't have a single flow, but there are several branches, you need to estimate the proportion of items that will flow along each branch. And this you can do by collecting data along a period of time. Since not all products flow through all steps, we need to know the proportion of the throughput entering the line which is flowing through each step. This is reflected in column O. All products entering the line flow through the first 3 steps, 100% in column O. In step 4, line 6, only the products which are not under warranty are processed, that is 80%. In line 7, only products to be returned to the customer without repair are processed, that's 4%. In the repair step, line 10, 100% of products need to be repaired, but some products more than once, those failing functional or burning test. 119% of products need to be processed. We are going to calculate the staffing required full-time equivalent for each process step in cells M4 to M13 using Solver. In order to balance the line, we need the right staffing on each step to ensure enough capacity to handle the product arrivals. This means that cycle time should be less or equal than inter-arrival time. Cycle time is equal to average time times percentage throughput divided by staffing. We calculate the total staff required in the line in cell M1 by adding all the yellow cells in column M. This cell value is what we want to minimize as long as we meet the requirements that all cycle times P4 to P13 are below the inter-arrival time in K3. We are adding the constraint N4 to N13 greater or equal than 0.1. The proposed staffing by solver in the yellow cells M4 to M13 is shown above, which gives a total staff of 13.3 in cell M1. This is a theoretical minimum which assumes all staff has all skills, which is not usually the case. In cells D1 to H1, we obtain the compound for each process participant. Some perform several operations. These values are obtained from those in column M. If receive and coordinator can be combined, we may have to round up the sum of the two from 1.6 to 2. We simulate this by increasing the values in the yellow cells of column M. Invoicing, we round up from 1.8 to 2. Test from 2.9 to 3. And repair from 7.4 to 8. This manual rounding will lead us to this situation, where the total staff has increased from the theoretical 13.3 to 15 after considering the different skills required in the different steps. This increase in the staffing has an effect in lowering the cycle of the steps affected below the takt time of 5 minutes. Looking at the percentage throughput column, we notice that some steps only process 4% of the products to be repaired, while test and repair have to process 119%. The reason for this is that only 80% pass the test OK the first time. This means 20% have to be retested a second time. Same with burning, where 5% fail and have to be retested. When we visit Gemba to collect process times, we can collect also the number of products waiting to be processed before each workstation. This is WIP, which is in column Q of our chart. Q1 has the total WIP in the line. Every product arriving to a workstation will have to wait in the queue until it is its turn to be processed. Column T has the lead times for each product to be processed on each workstation, taking into account the length of the queue. This is calculated with Little's law. Lead time is equal to WIP times throughput. T1 has the average total lead time in hours for one product from the time it is received from the customer until it is returned repaired. Column K has the average process times for each operation. K1 has a total average process time for the product, taking into account that not all products go through every process step, as shown in column O. In this case, it is 66 minutes. Just now, the average lead time to repair a product is 15 hours, as shown in T1. Out of these hours, we're only adding value for 66 minutes, total process time, as shown in K1. The rest of the time is waiting time along the different workstations, which is non-value add. The difference, lead time minus process time, is equal to 15 hours minus 1 hour 6 minutes, equal to 13 hours 54 minutes. Is the non-value add time. The ratio value add time to non-value add time is therefore 1 hour 6 minutes divided by 13 hours 54 minutes equal to 77.9%. We must bear in mind that the WIP data we have collected from Gemba has typically a lot of variation. So this ratio we have calculated may vary widely depending on the moment we visit the line. This is why we need to collect variation data and use simulation to get a more realistic picture. A value stream map allows us to understand who does what and when. We should build a map after a visit to Gemba, where things are happening, to make sure it represents the current reality. One alternative is to make the VSM directly in a spreadsheet in the cloud, where all team participants have write access. Typing into the smartphone is a common skill nowadays, which we can use for data entry into the VSM. Both process description and data can be easily typed or entered with voice with any smartphone. This VSM in the cloud can be easily shared with other process participants in order to validate it. After validation, all those with a need to know may be given read access to be able to consult it at any time. When it comes to implementing improvement actions, we can easily keep track of the new versions of the VSM as it evolves. Process data collection directly into the VSM can be validated the moment it is entered to avoid data entry errors. Analysis of the value stream data can easily be done in the same spreadsheet using Excel data analysis tools. To understand the effect of variation in the value stream, we can easily convert our VSM into a simulator.